So in the last video, we took a look at units and had some basic idea of how to start measuring things. And now we're going to start to think about motion. And for now, what we'll do is we'll study what's called kinematics, which is just figuring out everything we can about motion without having to think too much about what it is that's making the thing move in the first place. So I'd like to introduce the idea of a motion diagram and maybe what sort of information we could get from that. So let's think, for instance, that you're walking down the street at a nice steady speed. Today we're just going to be concerning ourselves with steady speeds. So here you are starting to walk down the street. And what we can imagine is that every second a camera is taking a picture of the street. So in the next frame you would be here, and then the next frame, sorry I can't hurt your eye like that, in the next frame you would be here, in the next frame you would be here, and so forth. And we can notice that if we're taking a picture every second and you're going at a steady speed, the distance between each of these photos of you going along the street should be the same. All right, now let's think about somebody else. Let's say that somebody else was also walking down the street. So here's another street, and since it's somebody else, we'll make them red. And so this somebody else, as we capture pictures of them every second, the pictures of them are looking something like this. So let me ask you, do you think this person is going, the red person is going faster or slower than you? Pause the video for a second, we'll get back together on that. Okay, so hopefully we agree that this person, the red person, is going faster than you are. And this is because the time between these two pictures here is still 1 second. That's supposed to be a clock face. And just like here, the time between these pictures of you, is also 1 second. But you're covering less ground in 1 second than the red person is. So the red person is covering more ground in the same amount of time. So we would say that the red person is going, faster. Okay. So is there some way that we could make that more quantitative? And yeah, the first thing we can do is I can refer you to a result that will get developed much later in the study of physics, not in this course even. But it turns out that if an object is rigid, we can completely represent the motion of that rigid object as a combination of what we call the translation of its center of mass. Translation is just a fancy way of saying moving up, down, right, left, in, out, combined with a rotation about the object's center of mass. And this is something that can be proven. So for now, if we say no rotations for now. We can completely represent the motion by just plain putting a dot at your center of mass. We'll more rigorously define center of mass later, but for now we can just say if you're to lay down on a teeter-totter, if you had your center of mass over the fulcrum, the teeter-totter would stay balanced. Okay, so if there are no rotations, then we can just replace u with a dot, like this, located at your center of mass. And similarly, we could replace the other person with a dot, located at their center of mass. And then we can look at this, and maybe it's a little more readily apparent that the red person is going faster than you are, because we're covering more ground here. Okay. And so we can maybe even get a little more out of this. Let's imagine that we're launching a rocket. Actually, go ahead, pause the video for a second, and try to come up with a motion diagram for a rocket. Alrighty, so hopefully we're all back together again. And so if we're drawing our rocket here, assuming, so our rocket is launching, we know that it's going to start out on the ground, so this would be at t=0. And if you've ever watched rockets launch, they don't move very far initially. But every second, they cover more and more ground. So 1, 2, 3, 4, 5. This might be, say, t=5 seconds here. And so this would be our motion diagram for a rocket. Now, with actual real-world rockets, usually what they do is they start curving the motion over to match the Earth's rotation. But for now, let's just say that for some reason we need to launch the rocket straight up. That's what it would look like. Okay. Now, we're going to be using these motion diagrams to come up with more formal definitions of position and displacement. But for a quick moment here, I need to take a quick detour into the land of math and bring up the idea of vectors and scalars. A scalar is just a really fancy way of saying that it's just a number. And for a vector, you can say it's a number with a direction associated with it. So an example of a scalar, for instance, could be the temperature. We look outside, we say it's 20 degrees out, and that's all you need to do to describe the temperature outside. Or we could be talking about an object's mass. Whatever the number that gets read on the scale, that's the mass. Time's a scalar. All you gotta do is read the number off the clock, and that's everything we need to know about time. Well, what are some examples of things that we need to worry about direction with? Well, one of them would be position. We'll do this a little more rigorously in a moment, but maybe a way to think about position is, when you're going down a freeway, You know how they have the markers along the freeway every mile to tell you where you are along the freeway in case you get in an accident or whatever. You can call and say, hey, I'm at mile marker 27. I need some help. So what they've done there is they've made x or y equals 0 somewhere. In the United States, the somewhere is usually the state line. And then they decide that the numbers will increase in one direction and decrease in the other. So if you're talking about a north-south running freeway in the United States, the numbers start with 0 at the southern state line, and they increase as you drive north. So that's a reference to every, so that's referencing an agreed upon 0 location, the state line in this case. And positive numbers mean that you're north of the state line. Now, we could imagine a system where if you went south of the state line, the numbers would just start going negative. They don't officially. You restart it with the new state's numbers and jump the coordinate system. But we could imagine saying that as I drive south across a state line, that the numbers would just start going negative. That would be perfectly reasonable. And then positive would tell me I was north of the state line, and negative would tell me that I was south of the state line. So the mile marker number tells me how far I am from the state line, and then the plus and minus sign tells me if I'm north or south of the state line. Okay, we will be introducing shortly displacement. And that will similarly have a plus minus thing where we worry about direction. At the end of the day, did you end up to the right or to the left of where you started? So we have to take that into account. Velocity, that's another one. In fact, that's worth spending just a quick moment on. Because velocity and speed are related, but they're not the same thing. Speed is a scalar. It's just literally the number your car's speedometer reads out. It doesn't give you the direction that your car is moving. It just simply says how fast is your car moving. On the other hand, velocity is how fast and which way is your car moving. So, for instance, let's say you're driving around a clover leaf at 50 kilometers an hour. As you go around, so you just say, okay, my speed is constant. It's 50 kilometers an hour. On the other hand, the velocity is not. Because as you go around the clover leaf, first you would be going at, say, 50 kilometers an hour north. Then you would be, as you go around the clover leaf some more, you'd be going at 50 kilometers an hour northeast. Then 50 kilometers an hour to the east. And then 50 kilometers an hour southeast. And then 50 kilometers an hour south. And then 50 kilometers an hour southwest. And then finally 50 kilometers an hour west before you merge onto the other freeway. So while you're going around the clover leaf, your speed stayed constant, but your velocity did not because the direction kept changing. And for completeness sake, another vector we'll be seeing soon, not in this series, but soon, will be acceleration. Alrighty. So with that, I figured now's a good time to start defining position. I've already intuitively talked about referencing, say, a state line or something like that. So let's say we have a motion diagram for some object that's moving like so, for instance. A way that this in and of itself, just me drawing the dots, as long as I did it to scale, is a complete representation of the motion of the object. T equals 1, 2, 3. But if we wanted to hang a number on it, we could, and this is a very typical choice, we could decide that to place x equals 0 at the initial position of the object. We don't have to. There are plenty of choices that we could make, but that would be one choice. And then say over here at t equals 3 seconds, this would be, say, maybe x equals plus 5 meters. And how would I be interpreting that plus sign? It means that I'm to the right of the origin. Alrighty. But we didn't have to do that choice. Some other person could totally choose to make a different choice. So let's say the pink person here. The pink person might decide that this is their x equals 0 in pink land. Then this final position here would be equal to x equals negative 1 meter. And this would be x equals negative 6 meters. And I would be interpreting that negative sign as meaning that we were to the left of the origin. So position is, the value of a position is not necessarily something everybody will agree on. It depends on where you choose to put x or y equals 0. We could also, in the interest of completeness, we could also represent position with an arrow. Formally, this arrow would be called a representation of the position vector, but we don't need to get too fancy about it here. If I wanted to say represent the position here at t equals 3 seconds in the frame of the person that I drew in black, we just draw an arrow from the origin. Okay, let's do a little better job of that. Just draw an arrow from the origin to that point, and we would say that that is the position at t equals 3 seconds. You'll notice I stuck this funny little half arrow head over the x. That is a pretty common way of indicating this is a vector. So I could either say plus 5 meters, or I could draw, and the plus means to the right of the origin, or I could draw a arrow that corresponds in scale to 5 meters, pointing to the right. Those are both equally valid ways to represent the position. In fact, they are equivalent ways. And again, just for completeness here, this same position for the pink observer would be done the same kind of way. We would be drawing an arrow, sorry about that. We'd be drawing an arrow from the pink person's origin to, oops, come on, to the person's location. And again, the pink observer would label this again with an X with a funky little arrow over it. But now the arrowhead would be pointing to the left and to scale 1 meter. Okay. So I've kind of implicitly mentioned that we are interpreting plus and minus to mean to the right and to the left. And as far as that goes, that is a standard choice. But in physics, you are free to bend the rules. In math class, they would almost certainly be telling you, yeah, you want plus to mean to the right and minus to mean to the left. So if you don't say otherwise, we'll assume that plus means to the right of the origin. And minus means to the left of the origin. But you are free to write your own rules on that. If you want to say that you consider left to be positive, as long as you explicitly state that, most physicists will be okay with that. Okay. So with that, we can go into coming up with a definition for displacement. Now, displacement is kind of just a segue to coming up with a better definition, coming up with a definition of velocity, but it's an important step. So in one dimension, the displacement between two positions is defined to be the final position minus the initial position. Now there's a lot of notation here, so let's go and unpack that. Whenever you see me write one of these triple equal sign thingies, that just means by definition. When you see a delta, the capital Greek delta just looks like a triangle. That should be read as change in. So, and then you would say change in what? We've already said x, if it's right left, or y, if it's up down, is position. So this already gives us our first clue here. Displacement is the change in position for some motion. Now there are different notations for noting initial and final. Some people put little f's and little i's in the subscripts, but also very common is to just use an x all by itself for the final position. And here, you'll notice there's a little 0 as a subscript for the x. And in a nod to some of the British people who started developing this stuff, this is usually read as x naught. And it's not N-O-T, it's naught, N-A-U-G-H-T, which is just a fancy way of saying 0. So you could call it x sub 0, but everybody calls it x naught. And whenever you put a naught on something, that almost always means the initial value for something. So in this case, this would be the initial. That's what the naught subscript means. Initial what? The x means position. So our displacement is the change in position for some motion, and it's defined to be the object's final position minus its initial position. So its dimension is going to be dimensions of length, because all of these have dimensions of length. And typical units, if we're doing SI units, it would be meters or centimeters or whatever. If you want to work in other unit systems, say SAE, maybe you'd use feet. Traditional Russian imperial units, maybe you'd use arshins. If you want to get really old school, you could use cubits. Doesn't really matter. As long as that unit is a unit that recognizes length, that would be a valid choice. Now, when you add and subtract, though, you do have to make sure that the units match. So to start out here, let's think about some car driving down the road. So it starts over here. Yes, all my cars are super duper boxy. And yes, I've heard people say it looks like the top of Captain Crunch's head, so just deal with it. So let's say this initial position here, x naught, is located at +3 kilometers. So we'll say at x equals 0 is right there. And the final position, x, is -2 kilometers. Okay, what we'd like to know is what is the displacement of my car. Okay, well, we can go to our definition. We can say that the displacement is the final position minus the initial position. Now, when we substitute in values, you've got to be super duper careful here to keep track of the signs. So you're not free to just drop the signs, you got to keep them. So when we put in here, my final position is -2 kilometers, and I have to keep that. My initial position is +3 kilometers. So first off, when you are adding or subtracting two numbers, you have to make sure that the units are compatible. They have to be exactly the same units, including matching prefixes. So here we've got kilometers, there we've got kilometers. The units are compatible, so we can go ahead and finish this up. And if they weren't, we would have to do some unit conversions first. And we can say -2 minus 3 is -5 kilometers. And so how would I be interpreting this? I would be interpreting this minus sign, again, as meaning that we displaced to the left. So I can go ahead and draw my displacement arrow. It would look something like that. It would start here and go to here. And so a way to interpret displacement is to say that it is the recipe for how to go in a straight line from the initial position to the final position. So in this case, at some later time, this car ended up 5 kilometers to the left of where it started from. Now, there's an important warning here. Displacement is not the same thing as distance traveled. For instance, let's look at this case here. Let's just say we've got a hockey puck or something that's going to the right. We'll just put it initially here at x equals 0 and over here at x equals 1 meter. Again, we can figure, so this would be x naught equals 0 meters. So again, we can figure out the displacement, x minus x naught. That will be 1 meter minus 0 meters is +1 meter. So that would be telling me that my displacement was to the right, like so. And that this distance was 1 meter. Alrighty. However, was this the actual path that the hockey puck took? No, it was in the middle of a big, huge frenzy of passing that was happening between a lot of players. And so the hockey puck first went over here, and then it went over there, and it looped around like that, and eventually it ended up back there. So the actual distance traveled, if the puck had an odometer, would be much bigger than a meter. So displacement only tells you how to get from where I started to where I finished in a straight line. It does not care about the actual path. Okay, with that, in the next video, we will use that to start to develop a definition of velocity. So catch you in the next one.